morning, everybody. It's a pleasure and an honor to introduce to you Professor Lisa Randall from Harvard. And I don't think she needs an introduction. The only fact I can quote is that one of her papers, a large mass hierarchy from a small dimension, has been cited this morning, I checked, 3,668 times. Professor Randall, please.
Okay, good morning. Can you hear me? Okay, good. Okay, so I wasn't quite sure who to orient these lectures to, so I'm going to try to cover a broad range of ideas related to warp geometry. And for this audience, of course, I particularly want to focus on what I think it's important to look for at the Large Hadron Collider and how we should be preparing for that. I think it's just important to remember that as theorists and as experimenters, we have some important challenges. And I think one of the general points that I want to keep making is that a lot of effort has been gone into optimizing existing searches. People think about low-energy supersymmetry, for example, and how well can we do in terms of even determining mass parameters, doing as detailed searches as possible. But there are very important other questions to be asking, which have to do with what is the range of possible signatures we can hope to see. That is to say, it would be a real pity if there were things that were happening at the Large Hadron Collider that we hadn't anticipated, and therefore we hadn't actually tried to extend our searches to look for that. And one of the most important aspects of that, I think, is going to be trying to really extend the energy reach of LHC. I mean, it could turn out that I'm totally wrong in the first year we see everything and it's all light and it's easily accessible. But it could be that some of the most interesting particles or phenomena happen at the limit of what the Large Hadron Collider can find. And so I think it's very important to be anticipating the full range of signatures so that we can really see what are the possible things that we can do. And that is one of the reasons, really, that we do model building at this point. It's not, I mean, one reason is we're trying to make these theoretical connections and understand what gives rise to the various mass scales we have in our theories, for example. But really, another reason is because if we have models, it's a concrete way of saying what are the kinds of signatures we can hope to see. And sometimes we're surprised by what are the things that might be possible to find at the Large Hadron Collider. So at lower scale, most of you have heard about supersymmetry. Little Higgs models is more recent. But at higher scales, we want to think about strongly interacting theories. And I think extra dimensions is one way of thinking about strongly interacting theories. Theories that might involve heavier, even broader objects that could occur at higher energy scales. And so that's going to be the focus on my talk, is extra dimensions. And I think as a bonus, we might have some insights into quantum gravity and strongly interacting physics, as I'll try to make clear. So the outline of, I have 3 talks, so the outline of what I'd like to do, we'll see how far we get, is the first talk will have a lot of introductory material, just an introduction to the type of warp geometry and extra dimensional model I want to work on, or want to think about. And I'll talk about why we think about it, what the original model is, and what it is that we can look for, in particular the KK resonances, Kaluza-Klein resonances, that decay into electron-positron or muon anti-muon pairs, which should be a very, very clean and nice signature of these models that should occur quite early on if the KK mode is light enough. Then I want to turn to bulk RS, and by that I mean a variation of the model. And we'll see what I mean as we go along, but a variation of the model where the signatures can be quite different and the reach could be quite different. And it has the same mechanism involved as far as the hierarchy problem goes and as far as the particle physics problem we're trying to solve, but it has a very different signature. And we'll see that it's really important to think about that. And in particular, just to anticipate, one of the most important lessons from this search is that it's going to be very important to find ways to identify and distinguish energetic top quarks. And the reason I'm saying that now before I even get to it is because even if you don't believe our model, even if this model has nothing to do with what's going on, energetic top quarks might be one of the best ways to probe the electroweak sector. as everyone knows, the top quark is the heavy quark, which means it is most strongly interacting with whatever it is that breaks electroweak symmetry, which means that we want to study tops in detail. And by studying in detail, I don't mean just measuring the mass as accurately as possible. I mean being able to distinguish tops up to as high energy as we can possibly get to. And this is something that I think people have started to look at, but there's really a lot more work to be done. I gave a talk about this recently, but I do want to have time to also talk about so-called black holes from extra dimensions. The point there is going to be that I really doubt we're going to see black holes, but there are interesting signatures having to do with strongly interacting physics that I think it is well worth probing. And in particular, compositeness studies as a function of energy can give a lot of insights into what's going on. And what I'd like to do in the remaining lecture, if there's time, is talk about flavor from warped extra dimensions. Because in a lot of recent work I've been doing, it really seems that this warped extra dimensional geometry provides not just a tool for solving the hierarchy problem, but conceivably for explaining the hierarchy of masses of quarks and leptons that we see. And if so, there's a lot of insight to be drawn there. And again, this gives some very interesting things that we should be looking for. In particular, and again to anticipate for those of you who don't make it through all three lectures, I think flavor-changing top quarks decays could be really interesting, like top to charm Z, which is predicted to occur about the level of 10 to minus 5 in these models, which again might be at the limit of what we can see, but it's a very, very interesting thing to look for. Okay. So that's just the outline of the talks. Now I'm just going to start with some very general introduction of why we're even thinking about extra dimensions in the first place, and then I'll go on to discuss the hierarchy problem, in particular the RS1 solution to the hierarchy problem. Let me also say, I know these are lectures, but if people have urgent questions, please feel free to interrupt, because the lectures will build on themselves, and if you get lost early on, you're not going to be able to follow the rest. So feel free to interrupt, I don't mind. If we don't get through all the material, I'm not bothered. Okay, so why do we think about extra dimensions? Well, you've probably heard this before. I'm going to run through it quickly. But one of the reasons is string theory. String theory does tell us that there should be extra dimensions. It doesn't mean that there are extra dimensions that we can see or that even have visible effects. But from a point of view of particle physics, the reason they're so interesting is because they can illuminate connections among observable quantities and show solutions that we had not anticipated to very major problems, the hierarchy problem being the most prominent, and I'm going to focus on that one in the talk. And the other reason, of course, is that we don't actually know how many dimensions there are. General relativity, after all, works for any number of dimensions. And the only way we're going to know about the existence of other dimensions or what their consequences can be is if we really just try to investigate the possible consequences. Plus, as a bonus, by thinking about extra dimensions, and this is a very important point, by thinking about extra dimensions, people have found new solutions to particle physics problems, even in the context of 3 + 1 dimensions. That is to say, by isolating what was the heart of the mechanism that was going on in some of these extra dimensional models, people have found new ways of thinking not just about higher dimensions, but even about 3 + 1 dimensions. And there's been a lot of new results in the last 10, 15 years about extra dimensions. And I think it's just important to emphasize that we have found new theoretical connections, but also new possibilities for what to search for experimentally. And a particularly interesting signature that comes out of warped extra dimensions are the new resonances I'm going to talk about. And so I think it is really critical to explore these theoretical and experimental implications. Okay, what's new? Why did people start thinking about extra dimensions again recently? After all, the idea had been around since the 1920s. Well, I think the most important new ingredient in terms of extra dimensional theories was something called branes, B-R-A-N-E. Branes distinguish dimensions along the brane from those perpendicular to it. And so what is important about this is it's telling us that not all the extra dimensions are the same. I just want to backtrack and just say that this part of the talk is very introductory. As the lectures go on, there probably will build on it. And by the third lecture, I'll really be presenting some new material. So I just want to say that this part is going to be very general, but then I'm going to build up to more specifics. So what are the important phenomenological implications of branes? Well, the first obvious one is that people talked about small extra dimensions for years. But they talked about small curled up dimensions. And now we know that dimensions don't have to be curled up. They can, in fact, be bounded by branes. And I have some very nice animations to tell you what I'm talking about. But before branes, it was just thought that we had to have curled up dimensions. And so again, it's hard to draw, it's hard to picture higher dimensional theories, so we resort to lower dimensional analogs. So here we have a two-dimensional universe, that is to say one infinite dimension and one small dimension. And the idea is that the small dimension is too small to see, it's curled up. The analog, of course, for our universe would be that we have many dimensions potentially, but we have three infinite dimensions and the other dimensions are all small and curled up. And the idea is that if you're everyone can see the big dimension, but only a small or tiny bug or something with high resolution can see the small dimension. In fact, if you don't have that resolution, you'd never see that other dimension of size r. Okay? So there are small dimensions that you just would have no physical consequences for unless we have the tools to probe things on the order of that scale, on the order of RC, the compactification radius. Okay? And if we have branes, we have the possibility of just bounding things between branes. They don't have to be rolled up. So that's the first implication of branes. We could have small dimensions just bounded between branes. Okay? Everyone clear on that? Another implication is that not all matter necessarily travels in the extra dimensions. You can have branes, which are lower dimensional surfaces, in higher dimensional space. And you can have so-called brane worlds where objects exist just in those lower dimensional spaces. Now, why is that important? Well, it's important because one of the most important constraints in higher dimensional theories was that if you have particles in the bulk, then they would have Kaluza-Klein modes, which we're going to get to. I haven't talked about them yet. But the fact is you would be much more constrained if you had electromagnetism spreading throughout the extra dimensions than if electromagnetism was just stuck on a three-dimensional surface, a lower dimensional surface in a higher dimensional space. So extra dimensions can be much bigger than we thought. So the idea is that particles and matter can be stuck on lower dimensional surfaces, much as water droplets can be stuck on a two-dimensional brane in a three-dimensional world. The idea we have is called a brane world, where we have particles and matter stuck on a brane. And as we're going to see, there are various possibilities for how much of the particles, how many of the particles, how much of the forces should be stuck on the brane. They could be spread throughout the bulk higher dimensional space, or they could be on the brane. Now, of course, you're much more constrained when particles and forces, such as electromagnetism, are in the higher dimensional space known as the bulk. So this allows for a lot of new model building possibilities, the idea that stuff can be stuck on a brane. Okay, and that's what we're going to focus on today. Okay, is everyone clear on that? And the third possibility is that warping even permits infinite dimensions in the presence of brane. We have gravity localization. I'm not going to talk about that in these lectures, but I think it's important to recognize, and also the warping will play a very significant role in what I'm going to talk about. So I will talk about the warping. Okay. So that's just general extra-dimensional stuff, and now I want to connect it to physics, in particular physics that we see, physics that we've observed already, and physics that we can hope to test in the future. So I'm going to talk about what's known as the RS1 model. This is work I did with Raman Sundram. And the idea is to address something called the hierarchy problem of particle physics, which can be phrased in a couple of different ways. One of which is, why is gravity so weak compared to the other elementary forces we know about? Now, gravity might not seem weak in many ways, but if you think about it from the point of view of two elementary particles, if I had two electrons separated by a fixed distance, the force of gravity is about 43 orders of magnitude smaller than the force of electromagnetism. That is a huge, huge discrepancy. Now, you might be willing to accept that number, but as we know, in particle physics, it's a much worse problem than that. Because when we take into account quantum mechanics and special relativity, we find that these forces, even if we just say arbitrarily these forces have these very different strengths, the quantum corrections tend to try to equate them. Okay? And the way we see that is in terms of mass scales. And as we know, there are some very significant mass scales in the context of particle physics. One is the weak scale, which of course is the scale we're going to be probing in great detail, we hope, in the next 5 or 10 years. And that's down at about 250 GeV. And the other is the Planck scale, which is the energy we would need if gravity would have been comparable to the other forces. That is to say, if electrons had mass not of their real mass, but of mass something like the Planck scale, then the force of gravity would be comparable to electromagnetism. And there's about 16 order of magnitude discrepancy between these two mass scales, between the Planck scale and the weak scale. And even if we try to put that in by hand, we find that when we include quantum mechanical effects, those scales want to be the same. And that's the hierarchy of mass scales that the hierarchy problem refers to. And in fact, the only way we can do it in what's called the standard model with a single Higgs is just to fine-tune the theory at 16 digits of precision, which no one believes is really what's going on. Okay? So we think that this is a clue to some physics that underlies what's going on in the standard model, and that's what we're trying to explore. Okay? Now, this is something that most of you have heard probably about supersymmetry as one possible solution to this hierarchy problem. But the point is that once we include supersymmetry breaking, it's truly challenging to get everything to work out, including flavor physics, including the real Higgs sector of the theory. So it really is worth exploring alternatives. We don't yet know that supersymmetry is right. It might be right, but we want to see what other possibilities are. Even if supersymmetry is right, it could be that warping plays a role. But I'm not going to talk about that now. But we all believe that fine-tuning is unlikely, even if it happened at the Museum of Modern Art. Okay. So what is the solution that I'm going to be talking about today? I'm going to be talking about something called RS1, which has to do with warped spacetime geometry. Okay? So what is the model? So what is the setup? So the setup is rather simple. There are two branes, that is to say these brane-like surfaces I talked about, 3 + 1-dimensional surfaces inside higher dimensional space. So there are two branes and a single extra dimension. Okay? The thing that makes this theory interesting, however, is that the branes would naturally have energy on them. Now, if a brane had energy, it would want to either crumple up or expand, but we know our universe looks like a large flat universe. So how do we accommodate that? Well, there's also energy in the higher dimensional space known as the bulk. And as a competition between this bulk energy and brane energy, that gives rise to these large flat branes that we have. But once we have this energy that exists in the bulk and on the brane, you find that the solution to Einstein's equations of general relativity is very non-trivial. It's not just flat spatial dimensions, which is what people have thought about before, but it's something called warp geometry. So how can we understand warp geometry? Well, there's a couple of different ways. One is in terms of actually what the geometry itself is. So what I have there is the metric for the geometry. That tells us what space looks like. So let's just see if we can understand it a little bit. So suppose that e to the minus 2 sigma factor was not there. That a to mu nu is just telling you you would just have flat geometry. That is to say, everywhere in the geometry would be exactly the same. Y is the coordinate of the extra dimension, but sigma is actually proportional to y. It's a quantity k times y, where k is related to the energy that's in the branes and on the bulk, on the branes and in the bulk. So what we have instead of having just a flat metric is e to the minus 2ky times eta dx dx. And what that tells us is that there's an overall scale factor that depends on y. So at any given point y, you have a flat metric with a different overall scaling. Okay? And that's really one way of understanding this warp geometry, is that your scale is naturally changing as you go in y from one brane to the other, what I call here the gravity brane and the weak brane, sometimes called the Planck brane and the TV brane. Another way of understanding what warp geometry means is in terms of the graviton itself, the particle that communicates the force of gravity, which has the shape I drew there. That is to say, it also exponentially falls as you go from one brane to another. So just at a very intuitive level, this is one way to understand why gravity is weak. It's exponentially suppressed by the time you get to the weak brane. So instead of having a hierarchy of 10 to the 16th, in terms of the fundamental unit of energy, which is on the brane and the bulk, you need a very small extra dimension, about size 35 in terms of this scale. Okay? So these branes are rather close together, but we have this exponentially falling warp factor, which tells us that there can be this huge hierarchy with the relatively small extra dimension. Okay? Questions on that? Yes? Speak loudly, please. So we solve Einstein's equation. Right. So what we did is exactly what I said. We solved Einstein's equation of general relativity, assuming we had a large flat brane. Now, what that assumption means is that the bulk energy is related to the energy on the brane. Once you assume a large flat brane, you don't have very many possibilities. So once I assume there's energy on the brane, then that tells me what the energy in the bulk has to be in relation to that energy. And then you solve the equation. So the only parameter in this is the one parameter we had, which is the single energy parameter k. And when you solve that, that's the solution. Okay? Other questions at this point? Yes? Please speak loudly.
How many dimensions around the
Okay, so in this case, there's a single extra dimension. And it's important that we have what's so-called codimension 1 branes. That is to say, a single dimension orthogonal to the brane to get this very strong dependence on that extra dimension, to get this exponential. If you wanted to have this particular thing work with more dimensions, you would want to have intersecting branes or some dimensions rolled up and only a single dimension with the warping. Okay? Are there questions at this point? Yes?
Push the button.
Apparently, if you push the button, I can hear better, and so can everyone else. Okay, so what tells you the distance between the branes? Yeah, so that's an important question, and it's not. I don't have transparencies on that. But after we did our work, Goldberger and Wise showed how the distance between the two branes can be determined. And one way of doing that is by having a scalar field in the bulk, in the higher dimensional space. And there's a competition between the values that field would take on the brane. That's part of the assumption of their theory, that it had two different values, and the mass term. So the mass term wants to drive the branes apart because that would lower the energy. Keep the branes together because that would lower the energy. Whereas because of the two different values, the gradient term wants to drive the branes apart. And so a competition between those two can give rise to a stabilized situation. Now that's very important for a couple of reasons. One is that the stabilization turns out to be a number of order 10 very naturally. If the stabilization had naturally been some number like 10 to the 16th, this would have been kind of irrelevant. But that's not what happened. It's a modest number. The second thing is it's very important for cosmology that these two branes are stable, at least at the late stages of the universe, so that the universe really looks four-dimensional. So the stabilization mechanism is indeed critical. Okay. Other questions at this point? Okay. Great. Okay. So what I wanted to emphasize in this slide is that we really do have scaling across the fifth dimension. That is to say, the scale you have really depends on where you are. And that's true for anything that has a dimension. That's true for distances, which is what this illustrates. It's true for mass scales as well. So the natural scale that you would see for masses, if you're on the so-called gravity or Planck brane, would be of order the Planck scale, just like we assume in our universe, where we think Planck scale is the natural scale for things, and we have to explain why all masses are less than the Planck scale. That is the root of the hierarchy problem. However, if you are on the TeV brane, where things are rescaled enormously by this exponential factor, 10 to the 16th, the natural scale would be more like TeV. And that is the root of the solution to the hierarchy problem, and it's also the root of why there should be very interesting phenomenological consequences if we are on the TeV brane. Okay? So this is the first point, that the Higgs mass is rescaled. So let me explain that. Okay? So what is one way of understanding the hierarchy problem? Well, the way of understanding the hierarchy problem is that if there is a Higgs particle, its natural mass scale is the highest mass scale in the theory. Unless you have a symmetry reason or some other reason to keep the mass light, it's going to try to be as heavy as it can be. That's what quantum mechanics tells us. Supersymmetry addresses this problem by connecting a Higgs scalar to a Higgs fermion. And for Higgs fermions, we have a reason that masses can be light, namely chiral symmetry, which extends only to the scalar sector in the context of supersymmetry. Okay. But without supersymmetry, there is no symmetry reason that the Higgs particle mass should be light, and we would expect it to be as big as possible. What's fantastic about the warp geometry is that that statement depends on where you are in the context of an extra dimension. If you're on the Planck brane, you would expect the Higgs mass to be as big as the Planck scale. But if you're on the TeV brane, the weak brane, you would expect it to be weak scale. And the reason this happens is that you can see that in terms of rescaling. Basically, all mass parameters get rescaled. In the case of the Higgs particle, the kinetic term has two factors of the warp factor, this e to the minus kr. The mass term has 4, and so the mass gets rescaled. So I'll just show you that in an equation. So here, what we have here, and I'm going to sometimes scatter equations through for those people who want to see more details. The upshot is going to be this rescaling of the mass, but for those of you who want to understand that in a little more detail, what we have there in the first line is the Higgs kinetic term and the standard quartic term you're familiar with, the lambda h squared minus v squared term that gives rise to the Higgs vacuum expectation value and also the Higgs mass. Now the thing is, we expect this parameter v naught to be of order the cutoff scale of the theory, something like the Planck scale in general. Now what you see here, though, is in this warp geometry, we have these factors squared of gvis and gvis everywhere. And what that is the metric. That is the metric on the TeV brane, which, as we know, has this exponential factor in front. Okay? So when we include the effects of that metric, we get these exponentials. And as you see, there's a different exponential in front of the kinetic term, dh dagger dh, and the quartic term, lambda h squared minus v squared squared. Oh, you don't hear me? This isn't working? Oh, this is a pointer? Yep. This is the biggest pointer I've ever seen. Okay, so you have these two terms, the kinetic term and the quartic term. And then you can rescale to get the Higgs canonically normalized, that is to say with no funny factors of exponential in front of it. But when you do that rescaling, the consequence is that this parameter V0, this mass parameter, this single mass parameter you had in the Higgs potential, gets multiplied by this other exponential, with the consequence that you have a new scale V, which is the exponentially suppressed V0, which translates into the Higgs mass is not naturally of order m0 or v0. It's naturally of order an exponential, a suppressed exponential times m. Okay. So this is an explicit example of how your mass parameter gets rescaled. So the natural scale for the Higgs mass is not the Planck scale, but it's the TeV scale. Okay? Questions on that? Okay. So although I showed this explicitly for the Higgs particle, this is going to be true for any particle that's localized in this region. So any particle who has its wave function localized here is going to be naturally of order the TeV scale. And that's really important for experimental searches because that's what tells us that we should be looking for particles near the weak brane which should have TeV mass. And in particular, the particles that we're going to focus on that tell us about this extra-dimensional theory are called Kaluza-Klein particles. They're particles that are like the ones we know, but they carry momentum in the extra dimensions. And they're associated with only bulk particles. So in the scenario I just told you about, I assumed the entire standard model was living on the weak brane. Okay? The only thing that I assumed was in the higher dimensional space, the bulk, was gravity, which means that what we're going to be talking about are Kaluza-Klein partners of the graviton. That will be the signal that there's something going on in these extra dimensions. There's a graviton in the bulk, and there are Kaluza-Klein partners of the graviton, and that's what we want to talk about. Okay? Now, there are particles that carry momentum in the extra dimension, but we don't know yet that there are extra dimensions. So, because we know that E squared minus P squared equals M squared, what they look like to us are particles that don't have, not that, we don't see that it's actually momentum in an extra dimension. They look to us like heavy particles, particles with mass m. And that mass m is of order TeV. Okay? And that's what's important, which is that they're at the right energy for us to be able to search for them. Okay? So what we're going to have, of course, is that when we have the protons collide, what we hope is that we would make one of these Kaluza-Klein particles. But the really interesting thing about these Kaluza-Klein particles, these partners of the graviton, is that their interaction strength is much stronger than that of gravity. That is a really important point, so you should remember that. Because what happens is gravity, we talked about how weak it is. So the graviton has 1 over m Planck interactions. This Kaluza-Klein partner of the graviton has 1 over TeV interactions. That is to say about 16 orders of magnitude stronger. Because the same warping that told us that the masses are much smaller than we thought also warps any mass scale, including the graviton interaction strength. If you have a graviton mode that's localized near the weak brane, it has 1 over TeV interaction strength, not 1 over m Planck. Which of course is extremely important because it's telling us that instead of just having missing energy, this particle is actually interacting like a weak scale particle, which means that it would actually decay in the detector. So you can look for it like you look for other heavy particle decays by looking for the decay products, putting those together, deducing what was there in the first place. That is to say, what is its mass, and even by looking at angular correlations, what is its spin. So if we saw this particle, it would be a strong indication this is what is going on. Okay, so having said those words, I'm going to tell you just a little bit about how you would actually go about finding these Kaluza-Klein modes if you care to do so. Okay? So that's a general statement about what we're looking for. So what we're going to do to find the Kaluza-Klein particles is you're going to solve the equations of motion for a graviton. It turns out that the solutions are Bessel functions. There are two boundary conditions, one at each brane. One will tell you the linear combination of the two Bessel function solutions you have, and the second gives the quantization condition, which is why we know roughly what these masses should be given the parameters of the model. Okay? So first of all, this is the equation of motion. This is the wave function as a function of y, this coordinate of the fifth dimension, that's going to tell us what is the wave function in the extra dimension. That is to say, we expand the graviton in terms of momentum states. These are standard four-dimensional particles, but they have non-trivial shape in the extra dimension. That's what this psi of y tells us. And the goal when we want to find the Kaluza-Klein modes is to find what are the allowed masses and what are the psi of y's. What are the allowed masses that these particles can have and what are the psi of y's, the wave functions. Okay? And so you can find a new coordinate, which is essentially the exponential of y. And you can see sort of intuitively what's going on by rewriting the equation of motion in this way. And there's something we call the volcano potential, which has this form that it sort of exponentially decreases away from the gravity brane. But at the gravity brane, there's this delta function. This delta function tells us that there is a single bound state. That bound state is the zero-mode graviton, the particle that communicates the force of gravity. In addition to that, there will be Kaluza-Klein modes, and their mode depends on energy, because as you can see, this is decreasing. So as you have a fixed amount of energy, at some point you'll be able to have your mode oscillate. So if you find a mode of a given mass, it's going to basically be peaked in the region that that exponential tells you is possible. Okay. This is just explicitly what the Bessel function solutions are. Then, as I said, there are these delta function potential on the brane, which tells us what linear combination to pick. And then finally, we're going to have another delta function equation from the TeV brane, which is going to tell us the quantization condition. And what I want you to get out of that is that basically the modes will be quantized in the fundamental unit of the energy scale on the brane. Which means that not only should there be a single graviton, in principle there should be a TeV scale 1, a 2 TeV, 3 TeV. Of course, what precisely that scale is depends on this parameter k. So if we're unlucky, it could be 4 TeV, 8 TeV, 12 TeV, or even 5 TeV, 10 TeV, 15 TeV. Which is why it's really important to extend the search as high as possible. Not just to see multiple KK modes, but it could be that the lightest KK mode is a few TeV. Okay? So another important point is that there really are modes at every mass scale, but we're only interested in the ones that are localized near the TeV brane, the ones that have this exponentially suppressed mass of order TeV. And in that region, we would expect M, where M is the local cutoff, divided by K modes, where K was that energy scale. So it's telling us there could be a few modes that sit around a TeV. Okay. And this is just to say there can be a few modes here, but then there are modes in the rest of the bulk. It's just that those are going to be way too heavy for us to see. Okay. So what do we see? Well, we have this distinctive spectrum. And as I said, we also have this warped interaction. So when we solve for these modes, we find that they have 1 over TeV scale interaction strength, which is kind of amazing, because if we saw this, we wouldn't just be seeing extra dimensions. It would be the first quantum gravity particle we'd ever seen as well, because no one's ever going to see an actual graviton, which has 1 over M Planck interaction, but you can see the KK mode of the graviton, which has 1 over TeV interaction strength. So again, this is what we showed before, but now hopefully we understand it a little better. We have this KK particle that can decay into an electron and a positron, or a muon and an anti-muon. And we can hope to see it. So it's not just missing energy. The mode is decaying inside the detector. You can reconstruct mass and spin, we hope. Would be the first genuine signature of quantum gravity, as I said. The graviton is too weakly interacting to detect directly, but its KK modes are amply, strongly interacting, that we can hope to see them soon. And the fact that they're decaying into leptons is spectacular, because of course that's something that we can see very well. So it's definitely something people will be looking for. And these are just some old plots. There are some newer ones by Javuz, Yazzel, Hewitt, and Rizzo, just to say that there could be several resonances if it's quite light. You could hope to see them. The width depends on the parameter k. Right now, it looks like the reach for the mass should be about 4 TeV. So that's about how high we expect to go based on what people have done these days. And this is 2 different graviton modes. And this is to say that you would like to be able to look at the angle between the leptons that come out, because the angular distribution is the way that you can determine, do you have a spin 2 particle or do you have a different spin? Okay. So the upshot from all of this is that RS1 gives a clean TeV KK graviton signal, And I think it is one of the first things the LHC could at least look for. Of course, whether or not they find it depends on how heavy it is, will determine how much luminosity we'll need to actually find it. But spin 2 and a gap in the spectrum, the fact that the lightest particle is spin 2, is really significant. And it's a definite indication of warped extra-dimensional geometry. There could also be other strongly interacting TV physics, some of which we'll talk about, which can complement this measurement. So if this is really what's going on, and if the scales are sufficiently low, there can be a lot of interesting things to look for. And so that's basically what I want to say about this first RS1 model. What I want to do in the next part of the lecture, this lecture and the next, is talk about alternatives that can be somewhat harder to find, okay? And what it implies about search strategies. So let me again pause for questions to ask. There are questions about searching for RS1. Question in the back. Please press the button.
Yes. So can you go back and clarify a little bit your statement before about the scalar particle that is used to keep the stabilization? Because you talked about now KK modes, right? And you talked about them being the only thing we look for. But what about the scalar particle, if it has to be there to stabilize the two branes? No,
that's a good point. And the particle I didn't talk about, which I should have talked about really, another light particle that we can see is conceivably the radion. So the radion isn't the stabilizing particle, but it is sort of what's determining the distance between the two branes. And you're absolutely right. There could be some, I didn't have time to put everything into these lectures, but the radion is a particle we can look for. It's a light particle. It has interactions very similar to the Higgs. And so one of the challenges will be distinguishing the interactions of the radion from the interaction of the Higgs, which is going to be done primarily through the gauge sector, I believe. But that is another particle that people should look for as well. Absolutely. Okay. Other questions? Okay. So now what I want to do is talk about other warped models that can address the hierarchy and what will be the signatures of those. Okay. So the first one I'm going to mention is just two transparencies. I'm not going to spend any time on it at all. But I just want to mention, remember I talked about the two different roles that branes can play. They can bound the extra dimension, and they can also be where particles are localized, where particles are living. So it could be that there are two branes, but that this doesn't actually bound the space, that you actually have an infinite extra dimension. Now the reason you can get away with an infinite extra dimension is because of this warping. And I'm not going to go into it here. But this extreme localization of gravity tells you that you can actually get away with an infinite extra dimension as well. In which case, your hierarchy problem would have to be still solved with a second brane, if we want to explain this natural scale. But this second brane now sits in the middle of the space. It's not going all the way out, okay? It's not the boundary of the space. This is work I did with Joe Licken, okay? So this brane is not the boundary of the space, it's just sitting somewhere inside. And the consequences are quite different, so I just want to mention it. Because what happens when you have this infinite dimension is that you don't just get KK modes that are localized that are TeV scale. You actually get arbitrarily light KK modes that are localized further and further out in the extra dimension. So when you produce this TeV scale KK mode, it actually decays not into visible particles, but into other KK modes of the graviton, which means that in this case, it would be an invisible decay. So the searches you've probably heard about for looking for large dimensions involving missing energy, that is to say the KK graviton just goes off and carries away energy you don't see, would apply for this case as well. And in fact, you can show that this energy scaling is exactly like if there were 6 large extra dimensions. And so this energy would just be missing energy, and it wouldn't be resonance the way I talked about earlier. Question over here.
Could the heavier KK modes decay to a lighter KK mode that is localized on the weak brane at all, and then therefore it be a visible signature?
Well, the thing is, even if it decays to those KK modes would still decay in turn to other invisible things. Right. So I think
why would they not then decay leptonically?
They can. It's just the branching fraction is lower. It's just
because you have this infinite extra dimension. Okay.
Yeah, it just looked like it probably would not be visible signature. Okay. Other questions on these two transparencies? Okay. In that case, I'm going to go on and talk about another variation, which has to do with what I said earlier, that this extra dimension is quite small. Okay? So the question is, do we have matter in the bulk or on the brane? So far we've considered a model where all the standard model particles were on the brane. So we focused on the lepton decay signature, but actually the graviton decayed into quarks, it decayed into leptons, it decayed into all the standard model particles. We focused on the leptons, of course, because that's the cleanest signature. Okay? However, it's not necessarily true that all the standard model particles are on the brane. This model, the warping I talked about, can solve the hierarchy problem. The fact is, you only need the Higgs particle to be on that brane. If the Higgs particle is on the brane, we get a warping that sets that mass to be TeV scale, but all the other standard model particles can be localized in the bulk or on the brane, including gauge bosons. You might have thought it's dangerous to put, for example, electromagnetism into the bulk, because what that does is it dilutes the force of electromagnetism. So if you had very large extra dimensions, you couldn't get away with that because the force of electromagnetism would be far too small. But since we have this extra dimension that's only about size 35, it's perfectly fine to put the gauge forces in the bulk because the dilution is not that much. Okay? So the first thing that makes this possible is that the size of the extra dimension is just small. It's so we don't dilute the force of electromagnetism for QCD too much. The other reason we can get away with this is that we only need the Higgs on the weak brane to address the hierarchy. After all, the hierarchy problem was just a problem about the scalar particle of the theory, namely the Higgs. Okay? In addition to that, there are actually reasons it seems that it might be useful or even preferred to have bulk fermions and gauge fields. Okay. One reason is that although the four-dimensional cutoff of your theory is TeV scale, if everything was sitting on the TeV brane, your cutoff would be TeV. For the full five-dimensional theory, the cutoff is more like the Planck scale, which allows for high-scale unification. Okay? I'll show a couple of transparencies on that. Another reason is that there's very interesting model building. That is to say, we have a chance of explaining and even understanding fermion masses and mixing angles. And if these are right, we're going to see that we're going to have to consider very different search strategies to look for these gravitons from the bulk or other particles in the bulk. Okay, so the first point is about unification. This is the same KK plot I showed before, but what I want to emphasize is that the reason we focused on the TeV scale was because that's where we're sitting. We live here at the TeV brane. That's where our experiments are going on. But in principle, there could be particles at every energy scale, all the way up to the Planck scale. Remember, there was this warp factor, so the cutoff goes higher and higher as we go to the Planck brane. So we do have high scales in the full five-dimensional theory. Not in the four-dimensional theory, which sits here, but in the full five-dimensional theory. So you can actually get the same sort of logarithmic running, that has to do with the warp geometry, that you get in a true four-dimensional theory. So you actually can get conventional unification. It cannot be predicted at the level that you predict it with low-energy supersymmetry, but it certainly looks as if the couplings converge, and it certainly allows for unification, which was one of the things that was said against extra-dimensional models in the beginning, but that's not true in this bulk model. The other thing that we're going to really focus more on, and in the third lecture I actually hope to talk a lot about this, is the fact that you have the possibility of explaining and understanding light fermion masses. And that has to do with the fact that, remember, we said the Higgs has to be here. This is where the TeV brane is. And what do masses come from? Well, quark masses come from fermions interacting with the Higgs particle, which is to say it has to do with how much their wave functions overlap. So if this is the shape of a top quark wave function, it's highly localized in the same region the Higgs particle is localized, which means you would expect the top quark to be heavy. Whereas for the light quarks, they're localized in this infrared region, so you would expect the light quarks to be light because their wave function doesn't overlap a lot with the Higgs. So if you have different shapes for these particles, wave functions as a function of the fifth dimension, you can naturally explain quark masses. And the way that goes about, and as I said, I'm going to talk about this a lot more in the third lecture, is that it's really this mass parameter, the mass of those bulk particles, that determines where it's localized. And it's very simple. I'm not going to go through this in detail now. I'll do it more in the third lecture. But there's a simple bifurcation. If the mass is bigger than some critical value, it's localized here. If it's less than that critical value, it's localized there. It's as simple as that. And that's what determines whether you have a big mass or a small mass. So this is important to keep in mind because any model that naturally explains quark and lepton masses is going to have the only particle that's localized here be the top quark, the right-handed top quark in particular. The left-handed top quark will have some relatively flat profile, and all the other quarks you would expect to be localized in this region. Why is that important? It's very important for phenomenology because remember we said the particles we're interested in are the KK modes that are localized over here. What that's telling us is that those KK modes interact mostly with the right-handed top quark, the same way the Higgs interacted mostly with the right-handed top quark, because it's localized in this region. So these KK modes will interact primarily with the top quark, much less with the light quarks, which, as you can imagine, is going to have very important implications for phenomenology. Okay? Questions at this point? Okay. So that's what we're going to consider now. We're going to consider this bulk version of RS1. So we're going to have the hierarchy before. We can have flavor and unification. But there's really important differences in the phenomenology, which is what I want to talk about. On the good point, on the one hand, there's a richer spectrum, which might be good because there's more things that we can conceivably find. There are KK modes of weak gauge bosons, of gluons, of fermions, as well as graviton that we talked about earlier. On the other hand, though, there's going to be a lower production cross-section for the graviton because the light quarks are localized far away, and we're going to see the gluon interaction is also smaller. Plus, and this is a really important point, the decay is primarily into right-handed top quarks. So if we want to find these things, we're going to have to be able to find these right-handed top quarks. So all these things are going to change the search strategies dramatically. So we've talked about looking for RS1 through this very simple channel of mu plus, mu minus, E plus, E minus. Now we're going to talk about this more complicated variation. And it's not just idle speculation, as I've argued just now. It could be that the model we really expect has particles in the bulk. Okay? So before I go into that, it's important that we understand what all these particle wave functions look like. I showed you a moment ago what we expect for the quarks. What about the graviton and the gauge bosons? Well, the graviton, like before, is localized at the TeV brane, just like before. The graviton KK mode, that is, that we would look for. What about the gluon? Well, the gluon itself, that is to say the massless gluon that communicates the force, the strong force, is spread equally throughout the bulk. It's a completely flat wave function. We know that has to be the case because of gauge invariance. The gluon should know only about the charge, no matter where the particle is located in that extra dimension. So the gluon itself is completely flat. Okay? The gluon-Kaluza-Klein mode, on the other hand, is like the KK graviton, is localized mostly at the TeV brane, but there's a very important difference, and this is going to be critical for phenomenology. This KK gluon is localized here, but then it has this very flat shape. That is to say, it has a non-zero value all the way up to the UV. This was somewhat surprising to us. It can be understood in a dual picture through vector meson dominance. I'm not going to even talk about that here. I just want you to know that there is a non-trivial, non-zero value all the way to the UV. And the reason that's so important is it's telling us that this KK gluon is going to interact even with the light quarks at a not insignificant level. That's very important. You might have thought that the KK gluon is located here, the light quarks are located there. They never interact. It's not true. There's this very flat wave function. Okay? So the upshot is that we have a richer spectrum, but some of the things I told you about lead to a lower production cross-section for the graviton. Okay? So first of all, the light quarks are localized away from the Higgs, away from the TeV brane. So there's exponentially suppressed interaction between the light quarks and the graviton KK function. It's not going to be true for the gluon, but for the graviton KK function, there's a small interaction with the light quarks. So the only way you are going to make this graviton at the LHC is through their interaction with the gluons. Now that's non-trivial because the gluons now, remember we said, had this flat wave function. They're spread throughout the bulk. So the interaction of the gluons is not going to be full QCD strength. It's going to be suppressed by the size of the extra dimension, by the volume, if you like, of the extra dimensional space. So there's an interaction with the gluon, but it's smaller than it was in the original RS1 case because it is spreading through the volume. So this is to summarize the graviton interactions. You don't need to understand all of this, but for those of you who do, we have an interaction with the energy momentum tensor. The gluon interaction with the graviton, as we said, is suppressed by 1 over TeV, but it's also suppressed by this volume factor, which is what this RC is telling you. This is a factor of about 1 over 35. The interaction with the fermions depends on where the fermions are localized. If it's localized on the TeV brane, like the top right, it's order 1. If it's localized away, it's 0, and this got messed up, but this should have been just that it's suppressed by volume if it's completely flat. How much time do we have? Is it?
Another 5 minutes.
Another 5 minutes, okay. So what I'm going to do now is I'm going to try to conclude and tell you about the graviton interaction, which will be small, and in the next lecture I'll tell you about looking for the KK gluon, which is really promising. So I'll talk about KK gluon and black holes and strong gravity in the next lecture. Okay, so the features of the interactions, we had the suppression by the gravity scale, we had suppression by TeV scale, we had suppression by the volume, and the fermion behavior we already discussed. And the upshot is that the reach for the graviton is much, much lower. This is work I did with Liam Fitzpatrick, Jared Kaplan, and Lian-Tao Wang. The upshot, it's not surprising. We haven't put in any cuts. We haven't put in anything here. We haven't put in looking for the decay products. We've just said, what is the production cross-section? And because there's no interaction with the light quarks, essentially, and because the interaction with the gluons is suppressed, the reach for the graviton in this case will be much smaller. Okay? To anticipate, because we're going to talk about the KK gluon next, which will be much more promising, but I just want to emphasize that all these KK modes decay primarily into top right. That's what all this plot is showing you, is that the primary decay mode is going to be into top right. So even if you make this, even if we do have a light KK graviton of 2 TeV, we better be able to find it, which is to say we want to look for the right-handed top quarks in the final state. And again, this is to anticipate what we're going to talk about in the next lecture. If a right-handed top quark has about TeV, we could probably find it in the standard way. What is the standard way to find a top quark, to identify that it's a top quark and not some other QCD jet? Well, you look for the three-prong signature. You look for a top that decays into a B and a W, and then that W decays into either leptons, in which case part of it is invisible, or into 2 jets. Okay. So if you have 3 nicely separated final states coming out of that top quark, you can reconstruct that you had a top quark. What this is designed to show you, so this is asking for delta R, which is the angular separation between these guys being bigger than 0.4, so that we can really see that there are 3 separate objects. Now this is asking the question, what fraction of the events will have this separation bigger than 0.4? So if the graviton mass is 500 GeV, you see it's a fairly substantial fraction. And even if it's 1 TeV, it still is. But if we had been able to look for gravitons of 4 TeV, as we said, the production cross-section was too low for the graviton, but this method wouldn't work at all. See, because most of the events have delta R less than 0.5 or 0.4 in this case. So if we're going to look for heavy objects, which won't apply for the graviton, but will apply for the KK gluon I'm going to talk about in the next lecture, we're going to have to address this fact that the standard way of reconstructing top quarks will not work. Okay? But for the masses of 2 TeV, we're fine. This is to say, if you have enough events, you can do angular dependence to do some spin determination. Okay. So I think I'm going to pause here and say that this is telling us that the graviton is hard to look for. We can look for it conceivably up to about 2 TeV by looking for its decay into top rights. That would be not so exciting because it's very likely that the KK scale is higher. What this plot is designed to show that in these bulk models, there are other particles that have KK modes, namely the gauge bosons and the fermions. And it could even be that the KK mode of a gauge boson, such as a gluon, is lighter than that of the KK mode of the graviton. So that is a very interesting thing to look for. Its production cross-section will be much bigger, but it's going to also decay into top rights. And we'll talk a little bit more about that next time, along with quantum gravity signatures. So I'll just pause for questions at this point.
Okay, thank you.
Any further questions? Okay.
So it was beautifully clear.
Hi.
Hello, Lisa.
How are you?
Fine. Nice to meet you.
Yeah.
You come with me to
To CMS?
Yes.
Okay, fantastic. Hi, thank you.